Hey everyone, welcome back to the Foundry by Forge College. Let's jump right in. In our last lesson, we crushed it by executing a stage, deployment, and release. Now it's time for the next major milestone in our capstone project, integration and audit-ready documentation. We've got all these mechanical smart contract gears and we need to assemble them. But we aren't just building this for ourselves. Oh no, we're prepping this machine for the ultimate, most intimidating VIP it's ever going to meet, the smart contract auditor. So let's make absolutely sure they don't find any loose screws.
Okay, let's look at the master blueprint for today's explainer. We'll start with the integration challenge, move on to building a unified interface, standardizing our error codes, crafting those audit-ready logs, defining boundaries, and finally proving the whole thing actually works with some rock-solid tests.
First up on the drawing board, Section 1, the integration challenge. This is all about taking our isolated gears and finally snapping them together.
So up until now, we've been hyper-focused on crafting these highly secure individual components, right? We've got a deposit fragment over here, a withdrawal module sitting way over there, but right now they're just scattered across the workbench. We absolutely have to integrate these isolated pieces into one beautifully unified deposit withdrawal module.sol. You might be wondering, why go through the hassle? Well, leaving them separated creates some seriously dangerous interaction gaps. I mean, imagine having two different cashiers furiously fighting over a single ledger book while a huge line of angry customers just waits. It's totally chaotic, it's begging for errors, and honestly, it's a massive security risk we just can't afford. Which brings us to Section 2, building the unified interface. This is basically constructing the secure front door for our entire system. Unifying our code really means exposing just one single interface. And right behind that sturdy front door lies one of the absolute most important concepts you'll come across in Web3, the canonical balance. Think of this like the master ledger book, locked deep inside a heavily guarded, impenetrable bank vault. Our newly unified module? It's literally the only contract holding the key to that vault. If some external adapter wants to know the balance, it doesn't just guess or snoop around. It has to politely knock on the front door and ask our main module. Total order, zero confusion. Moving right along to Section 3, standardizing your error codes. This is all about how we fail gracefully. Now, what's really fascinating about this phase is deciding exactly how our machine is going to complain when things go sideways. Because let's be real, in Web3, things will absolutely break. Networks get congested, users make typos, liquidity just randomly dries up. We need our machine to complain predictably. You see that mythical auditor we talked about? They hate long, verbose text errors that just eat up expensive gas. Instead, we use normalized, compact hex codes, kind of like sketching out technical instructions with precise orange and dark green ink on a pristine beige patent paper blueprint. Notice how 0x01 flags a permanent insufficient balance, while 0x02 flags a transient liquidity shortage? Off-chain tools can read this instantly and deterministically, without any of that frustrating guesswork. Let's slide into Section 4, crafting audit-ready event logs. This is where we create our immutable paper trail. All right, with our errors standardized, we need to design the paper trail our machine leaves behind when things actually go right. In the blockchain world, emitted events are your absolute source of truth. And this is exactly where system documentation comes into play. You know, writing the Solidity code is really only half the battle. This documentation is the comprehensive operation manual that proves to the auditor that your system behaves exactly the way you designed it to. Seriously, they shouldn't have to blindly guess what a specific contract interaction was trying to achieve. You need to map it all out for them. So, to make those logs truly audit-ready, they need to include some very specific fields: the sender address, the transaction amount, and a unique transaction ID. Those are pretty standard, right? But check out this magic duo, balance before and balance after. By including both of these, we are giving auditors and automated bots the ability to mathematically verify state transitions entirely from the logs themselves. They can just look at it and say, okay, the balance before plus this new deposit perfectly equals the balance after. Boom, instant mathematical peace of mind. Next up, Section 5, defining boundary responsibilities, because we definitely want to prevent any system collisions. To stop our newly integrated gears from grinding against each other, we have to set some incredibly strict boundary rules. Because if responsibilities start to blur, that's exactly how you get exploits. So ask yourself this: if a transient failure pops up, like say that temporary liquidity shortage we just looked at, who actually owns the retry logic? Does the main contract try again, or is that someone else's job? If your main contract gets bogged down in endless retry loops, you are basically leaving the back door wide open for reentrancy attacks, and nobody wants that.
This brings us to a really helpful concept, the responsibility matrix. Think of it kind of like a high-end restaurant kitchen. The main module, that's your head chef. The chef stays in the kitchen, completely isolated, solely focused on securely cooking up the canonical balance and updating that master ledger. The external adapter, on the other hand, is the waiter. The waiter is out there talking to the customers, validating the orders, and handling any retry attempts if, say, a dish gets dropped on the floor. The chef never, ever leaves the kitchen. Clearly documenting this strict separation of duties is a massive green flag for literally any auditor looking at your code.
Finally, we arrive at Section 6, proving it with tests. Time to verify the whole system. So the absolute climax of our entire build is proving to the auditor that this mechanical marvel actually functions under intense pressure. Documentation is great and all, but it is totally meaningless if the machine just explodes the second you turn it on. Integration testing isn't just about collecting a bunch of satisfying green check marks in your console. It's a very rigid 4-step protocol. Step 1, you deploy external mocks to isolate the module. Step 2, you simulate not just the happy paths, but control disastrous failures. Step 3, you assert that your promised event logs actually fire off. And Step 4, you verify the canonical balance remains completely pristine even through all the chaos.
Let me give you a quick example. If a mock adapter is simulating intermittent transfer failures, your test absolutely must assert that the system emits this exact text code, 0x02, right after the maximum retries are exhausted. You aren't just checking that it failed. You are proving that it failed in the exact specific way you documented it would, leaving behind a completely flawless paper trail.
Ultimately, your final deliverable isn't just the compiled Solidity code. As the golden rule of auditing dictates, they need the event signatures, the field types, and the precise mapping to behavioral expectations. Your real deliverable is that beautiful markdown file that flawlessly maps your complex integration tests straight back to human-readable behaviors. When an auditor sees those expected signatures and then watches your test reproduce them perfectly while under fire, well, my friends, you've essentially won the battle.
By strictly following this blueprint, you've successfully built and documented a remarkably hardened integration module. You've taken all those scattered loose gears and locked them together into a unified, testable, and fully transparent machine. And this sets the absolute perfect stage for our next big phase, resilience testing.
Because think about it. Sure, your machine survives the happy path, and yeah, it handles our little simulated errors perfectly. But what happens when the network actively fights back? What happens under the crushing weight of high concurrency batch transactions or relentless targeted adversarial attacks? I'm going to leave you pondering that slightly terrifying reality for a bit. To dive deeper into hardening your Web3 systems against the great unknown, and to check out more topics just like this, head on over to forge.college. Keep building securely, and I'll catch you in the next explainer.